So here we go. 5A. 5A, well, here's outline. Here's the outline right here. 5A. Students know how to predict the voltage or current in simple direct electric circuits constructed from batteries, wires, resistors, and capacitors. I am going to talk a little bit about capacitors when we get to 5B. Okay, because that. But 5A, I'll just combine 5A and B here. And students know how to solve problems involving Ohm's law for resistance and capacitors and so on. Now, this is the review. This is what you already know how to do. If you have a certain resistance, a certain voltage, you get a certain current, I. So you need to know what these three things are: voltage, current, and resistance. Okay, voltage. Voltage is the energy that's in the charge carriers. You've got moving charge in these wires. They carry energy. How much energy? Well, that's what voltage is. It's the joules of energy for every coulomb of charge that the electricity is carrying. What is resistance? Okay, resistance is how much voltage I need to get 1 amp of current to flow through it. So resistance is really voltage, the voltage needed to get 1 amp. This is really kind of explaining it using units. The voltage you need to get 1 amp of current to flow through it, and a volt per amp is called an ohm, abbreviated with an omega. A joule per coulomb is a volt, abbreviated with a V. Now current is equal to the charge that goes by per unit time. And in units, that's coulombs. Remember, a coulomb is just a big basket of charge. It's our basic unit of charge. And it turns out to be like 10 to the 18 electrons or something like that. It's a big number. Coulombs per second. And what's a coulomb per second called? An amp, abbreviated with an A. So here's kind of this is kind of like what you would put on your quantity chart. Voltage with the units, resistance units, current. Now, the equations that relate all this is delta V equals I times R. That relates all of these quantities in a circuit. All right. Now let's talk about capacitance, because we didn't talk about capacitance at all. So this is a brand new thing. You might get one problem with a capacitor on it, but it's really easy. It's really easy. So turn your brain on, drink it all in, and don't be intimidated by it. If you put a battery and hooked it up, let's say we have a switch right here, and then we put in what's called, instead of a resistor, we're going to put in what's called a capacitor. A capacitor looks like this. It's just two plates of metal that looks like this. Now we don't actually draw it like this. The symbol for it is just, it almost looks like a battery, but it's just two parallel plates like that. This is the symbol for a capacitor, but this is what it physically is. These little tiny plates of metal separated. Now when you close this switch, here's our voltage. When you close this switch, this battery will push charges and it will fill up this plate with charge. Now it also extracts that charge from this plate, so you get a negative charge here, and in between them you get an electric field. Okay, that's what a capacitor is. Now what does a capacitor do? It does two things. This is a capacitor. Doggone it. A capacitor. It does two things. it stores up charge, and it stores energy. Now, we don't have time right now to talk about what a capacitor is used for. But they are very, very useful little devices. They're used to store energy and store charge so that we can use it later in a circuit. Okay, and your cell phones, your computers, all your electronic devices, we got capacitors everywhere. Okay, pay attention. Yeah, put that away. Thank you. All right, that's what you get for sitting in the front. Well, how do we measure capacitance? Well, first of all, when we close this, when this thing gets full, when this thing is as full as it can get, current stops flowing. And we've got energy stored in here, and we've got charge stored in there. And so what is capacitance, which we abbreviate with the letter C, is equal to the charge, and we'll call that Q. The charge that we store on this for the voltage that pushed the charge onto that capacitor. So this is a new equation for you. Capacitance is equal to the charge on the capacitor I get when it's full divided by the voltage. So what are the units here? This is coulombs. Am I still on camera? Nope. Coulombs per volt. And a coulomb per volt has a name. It's called a farad. Okay. Now, in AP Physics, a couple of you are going to take AP Physics next year. We're going to go over this in detail. I mean, we're going to spend a couple weeks on it. But we don't have time in this class, and it's not that important for regular physics anyway. But they're really cool. And I really hope some of you think about engineering. And electronic engineering and electrical engineering is fascinating stuff. And lots of great high-paying jobs are there. And it's a lot of work. I mean, college is hard if you're an engineering major. But the payoff is huge. And it's really interesting stuff. And you'll learn all about capacitors. But here's the equation. So you'll need to add that to your equation list. And on the final, it's on your equation list. But on your quantity chart, you have to add capacitance, and then the letter C, and then a farad, which we abbreviate with the letter F, and a farad is a coulomb per volt. Okay, so this would be in your quantity chart, right? Remember we did the quantity charts? And now you have to be careful, because the letter C, capital C when it's a unit is a coulomb, capital C when it's a variable is capacitance. And it's just charge you get on this plate over here per unit volt. All right. Now that's all the time I've got for capacitance. So just think about it and recognize it, and it's a pretty simple device. And whatever you get on your standards test in the final, it'll be pretty easy if you just know this basic definition. So study that. All right. So this is Ohm's law right here. I think we've covered 5A and B. All right, 5C. It's all about power. So just know that the power, well, power is energy consumed per unit time. You really need to understand that. That's joules per second. What's a joule per second? It's a watt, right? Now, but the equation is I times delta V. P equals IV. Now this makes sense, right? Look at this. This is a coulomb per second. This is a joule per coulomb. The coulombs cancel. I get a joule per second. That's a watt. Now, if you combine this with Ohm's law, remember that delta V equals IR. when you combine that with, you make a couple substitutions, you'll get this is equal to I squared R if I substitute for delta V. Or if I solve for I and substitute for I get delta V squared over R. So these are the equations for power in a DC circuit, direct current circuit. This is the power put in by the battery, and these two are the power that comes out of the circuit through a resistor. If you know the current in the resistor, go I squared R. If you know the voltage drop across the resistor, go delta V squared over R. And you've got the power. 5D. Transistors. Now talk about your factoid. This is just factoids here. But you should know about transistors. You should know about them because they're the most important electrical device to our digital computerized society. If it weren't for the transistor, we'd still be living in the 1940s and 50s. Okay, that would be the level of technology we would have, which ain't great. Okay? I mean, imagine life without a cell phone. There are probably hundreds or thousands of transistors in your cell phone alone. Okay? They put them on integrated circuits. Now, what is a transistor? It's a sweet little simple device that does one of two things. It acts as a switch. What does a switch do? It turns current on and off, doesn't it? I mean, that's what a light switch does. So, I mean, we have a light switch in this classroom. We turn the lights on and off with a switch. Well, a transistor acts like a switch, but inside a circuit. You can turn a current on or you can turn a current off. You can also, it also acts as an amplifier. It makes currents bigger. If you have a little current, it can turn a little current into a lot of current. Okay, now, here's kind of how it works. And I'm going to use the symbol for a transistor. It's kind of a complicated symbol. It looks something like that. Now, there are 3 wires. You can kind of see there's one wire, that wire, and then this one. If you put a little bit of current in here, if you put a little voltage on here, and therefore you put a little current on here, we say that it will turn on. Turns on. You know, when I got a little current in here. If I turn this on, then a lot of current can flow through here. But if this is off, if I have no voltage on here, and therefore there's no current on here on the bottom, it won't let anything flow through here. That's all it is. Now, how this works, the details of the chemistry, the electrochemistry that allows a transistor to work are beyond the scope of this class. We're not going to talk about it. But it's called solid state physics. It's a great branch of physics to go into. It's all about how integrated circuits work. Fascinating, fascinating stuff. And we humans are very clever. We thought of how to do that. Be proud of, you got to be proud to be human sometimes. Sometimes it's kind of embarrassing. Just watch the news most nights. It's kind of embarrassing to be human, but every once in a while we really come through with something cool, and transistors are cool. Now, if you turn this on, now here's how it works. Like, you've heard of a transistor radio, right? Well, it has an antenna in it, and what an antenna does is it absorbs a little tiny bit of energy that's in radio waves. And the radio wave interacts with the antenna and makes a little tiny current flow back and forth inside your antenna. Well, you hook up the transistor to your antenna. So you have a little tiny current flowing through here. Well, what does that allow to happen over here? It allows a great big current to flow. And that great big current can go to your speaker. And it can make, because you need a lot of electricity to make a speaker work. And so it amplifies the signal. You can't run a radio on just the radio signal that you get through the antenna. It's too weak. But we use transistors to amplify the signal. Now, in the old days, they used these things called vacuum tubes. Have you heard of vacuum tubes? They used vacuum tubes to amplify the signal. But vacuum tubes were big and clunky. They gave off a lot of heat. They would burn out. They weren't very reliable. And so when the transistor was invented, now all of a sudden radios became cheap and very tiny. You could fit a radio in a very small space. And it was awesome. It was just awesome. You could also use them as a switch. And this is where the miracle of digital technology comes in. If you turn this on, you apply a voltage here that allows current to flow. If you turn it on, we call that a 1. But if it's turned off, we call that a 0. And 1 and 0 are the two numerals we use in what's called binary. Have you ever seen a t-shirt? A couple of my friends have a t-shirt that says, there are 10 kinds of people in this world. People who understand binary and people who don't. Right? Because in binary, you only have 1 and 0. By the way, what I'm about to tell you is not on the test, but it's so cool I have to tell you. What is 0 plus 1? 1. What is 1 plus 1? It's 2, but the way we write 2 in binary, it looks like 10. But it doesn't mean 10. 10 is base 10. When 10 means 10, in base 10, you got 10. But in binary, which is base 2, when you have 10, what you really have is just 2. It looks like 10, but it's really just 2. Now, what is 2 plus 1? It's 3. So it looks like 11, but it really means 3. What is 3? Oh, what is 3 plus 1? It's 4. But now we have to use binary, and you kind of already know how to carry a 1, right? Well, what's 1 plus 1? 1 plus 1 is 10. Well, it's really 2, but we can call it. So carry that. Then what's 1 plus 1? And then what's 1 plus 0? That's a 4. 4 looks like 100. Anyway, there's a whole mathematics that involves binary numbers, and it's called Boolean Algebra. It's the algebra. It's the branch of mathematics that allows us to create computers. And it's really not that hard. It's weird. It's not that hard, but it's wonderful. And so anyway, I had to show you this, but you don't need to know this for the test. But you do need to know this. A transistor kind of looks like this. It's a switch and an amplifier. Okay. What's next? 5E. Okay, we already kind of went over this just really briefly. If you have charged particles, they apply what are called electric fields. Am I on screen okay? Yeah. Okay, so let's suppose I got some positive charge and I've got some negative charge here. Pay attention. If I put a little positive charge here, it's going to be repelled by these guys, isn't it? It's going to feel a repulsive force like this. But it's going to be attracted to these guys, right? Opposite charges attract. So if I put a little positive charge here, it's going to be attracted to that. So what's the overall force? Well, you add this force plus this force, and you get that force. And what I do is I just take my little test charge, I'm going to call this my test charge, and I just draw a line like this that shows the direction of the force that these charges apply to my little test charge. Now, of course, these charges apply forces to each other as well, but they also can apply, and so you get what are called field lines. Right? If I'm right here, if I'm a little test charge over here, I get repelled by them, but I'm attracted to them, so I feel a force that's in that direction. So this is an electric field. And these field lines just show you what direction a little positive charge is going to get pushed on if it's in that location in space. Okay? And so the electric field, the equation for an electric field, which we call E, is just the force on it and with the direction divided by my little test charge Q. All right. Now, if I've got two charges like this, what is this force between two charges? That's Coulomb's law, which we went over before. K, Q, 1, Q2, my two charges over d squared. D is the distance between them. Okay? And what is K? K, they'll give you K on the test. K is equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. Again, this is review. We already went over this. But that's 5E. That's what you need to know for 5E. Now we're going to get into some weird stuff that we haven't covered yet, and I apologize, we ran out of time. So I'm just going to give it to you, and hopefully you'll remember a couple of these things. And so 5F, magnetism. Okay, well, you played with magnets before, so some of this should be pretty easy. If I've got two magnets, I call one a north pole and a south pole, right, of a magnet. Now, what's true about these two magnets? If I put a north pole up against a north pole, what's going to happen? Are they going to be attracted to each other or repelled? They're going to be repelled. Like poles repel. It's kind of like charges repel, but it's different. Now, this is going to send magnetic field lines. They're going to repel each other, like get away, run away. Okay, so they'll look like that, the magnetic field lines. Now, they actually go back into the magnet over here, but they repel. Now, what happens if I put a north pole, south pole, south, north. Let's do the same thing, south, north. What are the field lines going to look like here? They're going to attract each other. This is going to go in here. This is going to go in here. They're going to try to pull each other together. Now, actually, magnetic field lines are a little different than electric field lines that I just drew. Magnetic field lines always come in loops. So what they're going to do, they're going to start at the north, go in the south, but they actually travel inside the magnet. Then they go way out here into the world, and then they come back in the other side. So they travel in way out here and come back into the other side. So those are magnetic field lines. So north and south attract, north and north repel, south and south repel. Okay? That makes sense to everybody? That's pretty easy, I think. And it's part of your everyday experience. Well, here's something that isn't part of your everyday experience, and here's where it gets weird. What creates magnetic field lines? Well, first of all, what creates electric field lines, right? Here's what creates electric fields. If I put positive charge over here and negative charge over here, I get an electric field, and it kind of looks like this. The electric field lines start at positive and end at negative, and what do? They apply forces to other charged particles. But what creates magnetic fields? These are magnetic fields, not electric fields. They're different. What creates a magnetic field? A magnetic field, magnetic fields are created by currents, moving charges. Remember that. What creates magnetic field? Moving charges. Well, now, you say, oh, wait a minute. In these bar magnets, there aren't any currents in there. Nobody's hooked up a battery to it. Yes, there are. There are currents in there. Now, I don't have time to go into the details of it. But magnets are made out of iron atoms. And iron atoms have electrons that are unpaired. Remember in chemistry you had paired electrons? Do you remember this notation like this? Like that? You had a paired electrons? That weird, what was that called? That electron configuration? Yeah. Okay. Well, iron atoms have electrons that aren't paired. And if you line them all up, they're all kind of moving the same way. They're spinning the same way, and they're circulating in the atoms the same way. Well, that's a circulating current. I mean, those moving charges act as currents, and they create magnetic fields. Every electron in your body creates a little magnetic field as it spins and moves around the atom. The problem is that your atoms in your body are all pointed, the electrons are all pointed in different directions. So the magnetic fields all kind of cancel themselves out. But in iron, lots of the electrons line up. So their magnetic fields add up, and so you get an overall magnetic field. So that's where these magnetic fields come from. But you can create a very strong magnetic field using currents. If you have a long straight wire, here is a wire, and you put a current through it, I. You can create, it's not a very strong magnetic field, but you can create a magnetic field nonetheless. And what does it look like? Okay, you're just going to have to memorize this. And by the way, I'm not going to talk about that. Here's our wire. Now imagine I've got a wire. Well, here's a wire. This is the audio cord. Okay, here's a wire. Now imagine this wire has current flowing through it to the right. Well, if that's true, there will be a magnetic field around it. And here's what the magnetic field looks like. It makes a circle around the wire that looks like that. This break in it means it's behind the wire. Now, oh, I drew it the wrong way. I can't believe it. So, here's what now, there is this way where you can tell what direction the magnetic field line is going to be. It's called the right-hand rule for wires. Grab the wire, take your right hand. Let me zoom all the way out here. Here's my wire. Take your right hand and grab the wire with your right hand, not your left. You get the wrong direction. And look how my fingers curl. See how they curl down like this? That means that the magnetic field is going to go down like this and then go behind it and come back up. It's going to make circles. Now, the farther away you are from the wire, the weaker the magnetic field. But whenever you have current flowing through a wire, you've got a magnetic field. Now, so this is the right-hand rule. So make sure you know the right-hand rule. Now, This is a fairly weak field. There's a way of getting a really concentrated magnetic field, really super strong. They're called electromagnets, right? You've heard of electromagnets? Here's how to make an electromagnet. Okay, get a paper towel tube. Well, we can use toilet paper tube. It's more fun to say toilet, I guess. So here's a tube. Okay. Now take a wire, and it's got to be a wire that's not a bare copper. It's got to be coated with plastic, or it's got to have insulation around it. And you take it, and watch this. This is really fun to draw. You wrap it around, and you send a current through this coil. It's called a coil. This is a coil. Also known as, more complicated term, is a solenoid. But all it is some kind of tube with wire wrapped around it. Now when you do this, here's what happens. It's amazing, and we study this in detail in AP Physics. So those of you in AP Physics, we're gonna get this thing next year. It's really amazing. There's basically these wires, the magnetic fields that these currents create in the wires, they kind of cancel themselves out here. But on the inside the tube, solenoid. Inside the tube, you get a really concentrated magnetic field, super strong. And it looks like this. And it acts kind of like a bar magnet, where this is the North Pole and this is the South Pole. Now, how do I know which way the North Pole and the South Pole is? Okay, watch this. This is, again, the right-hand rule. We use right-hand rules a lot in electromagnetism. It's very three-dimensional stuff. I mean, electromagnetism is very strange, but it's very real. I mean, the reason why motors work and all that is because of this. Okay, pay attention. Wake up, wake up, wake up. Look at me. Grab the tube with your right hand. Now, what's moving around in circles now? Well, with a long straight wire, the current was straight. The magnetic fields were going in circles. But in a solenoid or a coil, the current's going in circles, and it's the magnetic field inside that's straight. So when you use the right-hand rule with magnetism, your thumb is what's straight, and your fingers are what curls in circles. So grab that, let your fingers be the current, and notice that my right thumb points up. That means that's the North Pole and that's the South Pole. So figuring out where magnetic fields come from, we have to understand that magnetic fields come from moving charges, from currents. Currents is what causes magnetic fields to appear in nature. That if you have a long straight wire, you'll get a fairly weak magnetic field. Grab the wire with your right hand and watch your right fingers curl around. That'll tell you the direction of the magnetic field. Basically, the direction of a magnetic field. If I put a compass right here, it'll point in the direction of the magnetic field. Compasses point in the direction of a magnetic field. Okay, so it'll go up and then down, and, you know. But in a solenoid, what's straight is the magnetic field, but the currents curl around. So you grab it with your right hand, and your thumb points in the direction of north. Yes?
So is it like just straight field, or does it have a directional force? Like, does it go somewhere, or does it just stay in that?
Well, it actually, that's a great question. It comes out of the solenoid like this. It actually goes all the way around here and comes back in.
So would you use it to say, like, launch a projectile?
Oh, yes. Yes. They use, no, they do. Now, and again, because we're running out of time, we ran out of time this year, you can use what's called electromagnetic induction to create an awesome projectile thrower. Actually, the military has thought about, instead of using explosives, using electromagnetic induction to shoot a projectile. They just haven't mastered it yet. But, you know, the advantage is you wouldn't need an explosion to do it. Okay, now hold on. Don't put your stuff away yet. I'm not done. I got a few more minutes. So this is 5F. This is pretty much everything you need to know for the final. Now, last thing I'm going to go over. You've probably heard of this before in chemistry. This is 5I. Actually, I already went over 5G, the right-hand rule for straight wires and the right-hand rule for coils. You're going to have to look a couple of things up. Oh, one thing I can add it right here. The strength of the magnetic field, it's called a B field. Okay, that's the letter we use. It's measured in Teslas. Tesla is the unit for the magnetic field. Is a, wait a minute, why is that? Oh, right here, Teslas. I'm going to go over 5I really quick. You have 4 states of matter. There are 4 states of matter. Not 3, there are 4. What's the 4th one called? Plasma. So you have solids, liquids, gases, and plasma. Now, solid is relatively cool. You heat it up, you melt the stuff. Now the molecules are slipping around each other. They're still sticking together, though. You heat them up. They move faster. They move so fast they don't stick together anymore. Now they're a gas. Then you heat them up. You make them go so fast that when they smash into each other, they knock electrons loose. And now you have ions. Basically, a plasma is a gas that's so hot that it's made out of charged particles. Not complete atoms anymore, but ions. The sun is not a big ball of gas. It's a big ball of plasma. Okay? Now, last thing. Then I will shut up. Right here, there is a law that I don't have time to explain, but I want you to look it up. It's very hard to understand. It's called Lenz's law and electromagnetic induction. I want you to look that up. Look it up on YouTube. There's all kinds of videos and stuff. It's how to make an electromagnetic gun.